In black midwater, a small predator opens its jaws beneath a glow most animals cannot see. The deep-sea dragonfish carries a private searchlight, turning invisible wavelengths into a hunting advantage. Its mystery is not ordinary bioluminescence, which many ocean animals produce. The puzzle is how red light can reveal prey without announcing the hunter. If you descended beside it, that beam would likely remain invisible to unaided human eyes. Special cameras disclose what darkness hides, photophores emitting unusually long wavelength light. The dragonfish also possesses visual pigments capable of detecting those wavelengths. Together, emission and perception form a biological channel unavailable to much surrounding life. The hypothesis is elegant, but scientists must separate measured capability from unwitnessed attacks. Laboratory spectra establish light color, while anatomy and physiology reveal potential sensitivity. Stomach contents confirm predation, yet exact strike sequences remain rarely observed in nature. This investigation follows photons from their production to their possible consequence. It tests whether invisible illumination truly functions as covert vision rather than decorative glow. Every step crosses severe limits imposed by pressure, rarity, and darkness. The predator hangs motionless, carrying a lantern whose audience may be only itself. Dragonfishes, discussed here, belong to the deep-sea family, Stomiidae. Several Stomiidae genera produce red bioluminescence, including Malacosteus, Pachystomias, and Aristostomias. Species differ in anatomy and spectral output, so one mechanism cannot be assigned carelessly to all. Most oceanic bioluminescence appears blue because blue-green wavelengths travel efficiently through seawater. Many midwater animals consequently have eyes most sensitive to blue light. Red wavelengths are absorbed more rapidly, and sunlight's red component disappears near the surface. At dragonfish depths, natural red illumination is essentially absent, except from biological sources. This background creates an opportunity for a predator that can both emit and detect red photons. A dragonfish activates suborbital photophores, directing faint long-wavelength light ahead. A nearby fish reflects some photons, and specialized retinal pigments absorb the returning signal. Detection guides orientation, allowing the predator to approach before prey recognizes illumination. The consequence could be a shorter final strike and reduced warning. When you imagine the beam, avoid a bright red flashlight cutting visibly through open water. The emission is weak, short-ranged, and detectable only within physical and sensory limits. Water absorption restricts range, making the system useful for nearby targets rather than distant scanning. Dragonfishes possess elongated bodies, large mouths, and formidable teeth suited to seizing scarce prey. Some have chin barbels bearing luminous organs that may attract or inspect potential prey. Barbel form varies greatly, and its precise natural use is not documented for every species. A vibration or silhouette can trigger orientation before visual information refines the approach. The fish holds position, adjusts with small, thin movements, then accelerates over a short distance. Large jaws increase the chance of retaining prey after an energetically expensive encounter. This behavior fits a habitat where meals are unpredictable and missed attacks carry costs. The invisible light story becomes sharper inside the retina. Most vertebrate eyes use visual pigments built from an opsin protein and a light-sensitive chromophore. Some red-emitting dragonfishes extend sensitivity through specialized pigments and retinal arrangements. Malacosteus uses bacteriochlorophyll-derived compounds obtained through diet as photosensitizers. These compounds shift effective sensitivity toward longer wavelengths beyond ordinary vertebrate vision. Because the fish cannot synthesize them independently, feeding ecology supports the visual system. Evidence indicates the compounds ultimately originate in photosynthetic bacteria and pass through the food web. That pathway is biochemically remarkable, though intermediate dietary routes remain incompletely resolved. Pachystomias and Aristostomias use different retinal specializations, demonstrating more than one evolutionary solution. Spectral measurements confirm that long-wavelength emission overlaps with enhanced visual sensitivity. Overlap is essential because a lamp without a matching detector would offer little private illumination. Still, overlap alone does not film a hunt or quantify success in open water. Researchers infer function by combining emission spectra, retinal physiology, anatomy, and ecological context. The inference is strong, but it remains distinct from direct observation of repeated natural captures. Prey vision is another necessary part of the test. Many likely prey species lack strong sensitivity at the longest wavelengths these dragonfishes emit. However, deep-sea visual systems are diverse, and universal prey blindness cannot be assumed. Some organisms detect broader spectra or respond to faint light in unexpected ways. The searchlight advantage, therefore, depends on prey identity, distance, background, and photon number. At close range, even weak reflection may provide shape or contrast to the predator. At greater range, absorption and scattering erase the signal into darkness. A dragonfish must enter this narrow optical envelope before invisible light becomes informative. Motion, smell, mechanosensation, and blue sensitivity may help it reach that envelope. Red illumination likely complements other senses rather than replacing them. This layered interpretation avoids turning one adaptation into an all-purpose superpower. It also predicts specific observations that future field studies can test. The private beam connects predator behavior with the entire midwater food web. Organic particles and migrating animals transfer energy downward from sunlit waters. Dragonfishes consume fishes and crustaceans within this limited, uneven supply. A passing pressure wave prompts alignment, and faint illumination may identify the nearby source. The predator approaches, confirms a target, and converts stored chemical energy into a rapid strike. Successful capture replenishes reserves spent maintaining tissues, vision, and bioluminescent structures. Failure returns the fish to stillness, where low activity conserves what remains. If you follow those photons backward, their energy ultimately began with surface productivity. Even bacteriochlorophyll-derived synthesizers reach Malacosteus through ecological transfers across multiple organisms. The visual system is therefore not isolated hardware, but a dependency embedded in diet. Changes in prey communities could affect both nutrition and access to essential photosensitizing compounds. Ocean warming and oxygen loss can alter the depth ranges of midwater animals. Such redistribution may change encounter rates between dragonfishes, prey, and predators. Artificial light penetrates only limited deep habitats, yet expanding infrastructure could disturb some communities. Deep-sea fishing also samples dragonfishes, providing specimens while potentially biasing knowledge toward captured individuals. A trawl records presence and anatomy, but it cannot preserve normal hunting behavior. Vehicle lights may overwhelm faint emissions or provoke avoidance during observation. The tools used to see the system can therefore disrupt the system being seen. Conservation status remains difficult to determine for many deep-sea fishes because abundance data are sparse. Their apparent remoteness does not remove them from changing ocean chemistry and food supply. Invisible light reveals adaptation, but also the narrow environmental relationships supporting it. Understanding this sensory niche matters as changing midwater habitats rearrange predators, prey, and energy. Ultra-sensitive cameras could record red photophore use under minimally disturbing illumination. Spectral imaging might measure beam direction, range, and reflection from identified prey. Controlled behavioral work could test prey responses while reproducing pressure and darkness responsibly. Retinal studies can compare sensitivity among predator species and their actual prey. Together, these measurements could quantify whether red illumination improves detection or capture probability. No isolated spectrum can establish the complete ecological advantage. Repeated field sequences would need to show activation, approach, target response, and strike outcome. If you return to the hovering predator, the darkness now contains a measurable optical conversation. A photophore releases long-wavelength photons that seawater quickly limits. A specialized retina gathers the fraction reflected from something nearby. The fish may close distance while many prey remain poorly informed. That scenario is strongly supported by matched physiology, although natural hunts remain sparsely documented. Different dragonfishes achieve long-wavelength vision through different biological mechanisms. Their private light is neither magic nor universally invisible, but a constrained evolutionary advantage. In the final darkness, the dragonfish hunts within a red world that evidence supports but humans barely witness.